Hello. Today I'm going to tell you about the work we have done at Institute of Mathematics and Computer Science of University of Latvia on modular hybrid systems for gene regulatory system analysis. Hybrid systems can describe both discrete and continuous components of systems, and they are good for gene regulatory system modeling and analysis, as binding site occupation can correspond to these discrete variables, and substance concentration can be these continuous variables. If we think of this hybrid system model, it may contain just a partial information about the actual gene regulatory system, but an important thing is that this model can be analyzed mathematically, for instance, by finding all behavior attractors. And this way we can gain insights about the behaviors that are actually possible in this modeled gene regulatory system. However, if we want to analyze the hybrid system state space, we see that it can grow exponentially, and therefore this analysis can be very difficult even for a moderately sized system. And if we obtain some large state graph, it also may give just very little insight into the crucial factors that lead the system to one or other behavior. And therefore our contribution here is first recognizing possible modularity of hybrid system structure that leads also to modularity of the behavior. So some parts of the system becomes much simpler to analyze, as well as we develop methods for behavior choice point identification and visualization. A simple example is the Lambda Fog, which is a classical model of viral lysis and lysogeny switch. It consists of discrete variables or binding sites depicted here in this trapeze form. There are binary binding sites 0, 1, and ternary binding sites which can be empty or occupied by C1 or CRO, and these are this OR block and OL block, as well as there is a number of continuous variables or substances. The behavior of such a system works in a way that this binding site state, it determines the substance growth and degradations. There are formulas how this growth and degradation can be computed from the state, as well as the substance concentration conditions can trigger a binding site change. So if a substance grows and it reaches the threshold, this protein, it can attach to this binding site, making it bound instead of the free one. If we think of the behavior, an important thing is that if a substance which is growing and it can attach to several binding sites, in that case it's important which of the thresholds for these binding sites where the protein is to attach comes first in the course of the development of the protein. So for a growing protein, the binding site with the smallest threshold shall be affected first, and we shall see how this is important a bit later. But still, this gives us about more than 23,000 of symbolic states in such a simple example. So what we can do about it, I think, is we can look more carefully on this potential influence relation among these discrete and continuous variables, and we can see that there are regions in this structure which do not have any incoming edge, just the outgoing edges. So, and this means that this region, it cannot be influenced from outside in any way. So they are really actually independent. And this red region, I can say this core of the Lambda Fog, in fact, it is the one which actually determines already this lysis and lysogeny switch, and it has just 54 states possible in the reachability graph. But still, of course, this wider core and the full systems, they are needed to analyze the possible observational behavior. So this reachability graph of the core system, it can be printed on a single page, can be analyzed. So here we take into account these threshold ordering assumptions, which are biologically known. To build the graph, there will be a different graph for different threshold orderings. But still, we can look also at even simpler way on this graph, just by saying, identifying these attractors, which can be found. It is lysogeny and lysis, and the choice points for entering their basins, so where the fate of the virus actually is decided. We can look also on different threshold orderings. So in the case of core 1, this red part, there are just 36 options, and we can build these 36 reachability graphs. And if we look at the attractor structure in each of them, then we can identify that there are 4 equivalence classes of them. And then if we expand core 1 into core 2, then these equivalence classes are preserved, just this A further it can be separated in A1, A2, A3, or A4, which correspond to different behavior of these substances which are within the core 2 minus core 1 part. Then this analysis of threshold orderings, it allows us to identify the conditions which are needed for biologically valid lytic and lysogenic cycle, in addition to the biologically well-known assumptions about the protein ordering. So that's it. Thank you.